Okay, well, welcome everyone to today's SoFiE Seminar. I'm Andrew Patton, the organizer of the series, and today's speaker is Natalia Bailey from Monash University in Melbourne. Natalia is setting a new record for biggest time change to overcome to participate in this seminar. And her discussant is Simon Freyaldenhoven from the Philadelphia Fed, and he's setting a personal record for me for being the most local participant in the SoFiE Seminar to me here in Durham, North Carolina. So we're illustrating today the beauty of virtual seminar series. We'll follow the same format as before. The speaker will have 40 minutes, the discussant will have 10, and then we'll have 10 left over at the end for questions and answers. We'll finish at about the 1 hour mark. If you'd like to ask a question, you can use the Q&A button at the bottom of your Zoom screen, or you can raise your hand by going to the participant button and clicking on the raise your hand icon. Okay, with that, I'll turn it over to you, Natalia. If you'd like to share your screen.
Sure. Let's see. Okay. Right, so hopefully you can see that.
Yes.
Okay, well, thank you very much for the introduction, Andrew, and for the invitation. So the theme of today's talk relates to the factor model literature, and more specifically what we are interested in is being able to measure the strength of one or more factors that we are interested in analyzing. So we're going to discuss the importance of that from a theoretical point of view, and then what are the implications of having factors of differing strengths when we are looking at empirical examples. So this is joint work with George Kapetanius, who's from King's College London, and Hashem Pesaran, who's at USC, and Trinity College, Cambridge. Start off with a couple of facts about factor models that are of interest to us here. So clearly the literature is very extensive, and these models have been used in a number of areas. So two that we are interested in here are basically empirical finance, where here we're looking at being able to price potential risk factors that would be included in an asset pricing model. Or alternatively, you might be thinking of macroeconomics, where here the interest is basically capturing common shocks and how they propagate through the various segments of the economy. Key theoretical advances that have enabled these models to be applied to high-dimensional settings include contributions by Bailly, Eng, and a number of other contributors. Now, first of all, in terms of these common factors, many times these are latent, and as such, they need to be proxied, and typically these are proxied by principal components. And of course, you can have variants of that if, for example, you want to add dynamics to your setting. Now, the assumption when you're going to use these proxies is basically that these factors that you are analyzing are strong. And by strong, we mean basically that the impact that this factor has on the panel is basically fully pervasive. So it impacts all units. An additional difficulty is, of course, interpretability of the latent factor. So with that, this notion of factor strength, you can think of sort of relating it to the issue of identifying dominant units when you're looking at a network. So say that you have a production or financial network, then the interest is in identifying which are these units that dominate the network and how pervasive, how dominant are they. So in this case, you can have two settings again. One where you actually do have knowledge about the structure of the network. So for instance, you have access to input-output tables, and then you can use out degrees of the network, and that helps you to detect the dominant unit that acts as a dominant factor, as a strong factor. Here I'm giving a couple of, a few contributions in that direction. And on the other hand, of course, you might have cases where you do not have this information, in which case you need to come up with to detect these dominant units. So in a recent work by Capetanius, Pesran, and Rees, they look at this, they analyze this thresholding method, which basically allows them to detect pervasive units, if there are any, when you're looking at a large panel. And of course, this factor strength is also related to analysis of cross-section dependence. In essence, if you have a bunch of factors that have a specific strength, well, then this will translate in a certain structure of strength of cross-section dependence. An earlier work of ours, we proposed an estimator that basically quantifies the degree of this cross-section dependence, which we call it exponent, and we denote it by this parameter alpha. Now, this is based basically on the behavior of the variance of the cross-sectional averages of the units that we have in our panel. In a follow-up paper to that, we extended this approach, and instead of using the factor model as a vehicle to set up our problem, we actually looked at the correlation matrix that is implied by the units of the panel straight away. And basically what we were looking at was the proportion of statistically significant pairwise correlations, and built our estimator on the basis of that. In addition to that, we also showed that this method can also be used for residuals that come from panel data regressions. Now, even though they look at the degree, so the strength of cross-section dependence, this strength really what it picks up is basically the effect of the factor or factors that dominate the panel, the sort of effects within the panel that we are studying. So in this paper, we go a step further and basically look at how can we measure and estimate factor strength for each of the factors that we think contribute to this cross-section dependence. And we look at two cases, one where factors are observed and when they are not observed. Okay, so just to formalize a little bit what we mean by factor strength and how we sort of think about it. So let us consider a single factor model just as a start. We are assuming that n and t go to infinity, and basically we have that our units xit are sort of characterized by unit-specific effects, and then you have one factor which is observed for now, to which factor loading is attached for each unit I, plus an error term, of course, for which we assume it's IID and with heteroscedastic errors. Estimation of factor strength here, in essence, we are relating it to the degree to which this factor ft is pervasive. So what sort of effect does it have on all the units in the panel? So in essence, we are focusing on our attention on these loadings gamma I, and if one were to think of taking the sum of the squares of these over all the cross-section units n, then what we are interested in is the rate of increase of this quantity here with the cross-section dimension n. And so in essence, we have this rise, which is n to this power exponent alpha, and we call it alpha here. This alpha here, it ranges between 0 and unity. So you have a bunch of cases here. When alpha is equal to 1, this means that this quantity rises at the maximum rate of n, in which case this factor ft is considered to be strong. And this sort of relates to the latent factor model literature, which is what I discussed a minute ago, with key contributions by Yin. On the other extreme, you can have this exponent to be between 0 and a half, which means that basically this sum does not rise at a particularly very fast. In this case, you would consider this factor to be weak. And this area is what Onatsky studied in his 2012 contribution, where basically he shows that principal components in this case are inconsistent. And then you have this intermediate case where alpha is basically between a half and 1, which we call the case where the factor is actually semi-strong. Now this area here has not really received too much attention. From what we know, there are a couple of other contributions that we know of other than ourselves. One comes from our discussant, Simon, who basically looks at what happens to factor selection procedures when you are in this area of factor strength. So basically when the condition of alpha is equal to 1 breaks down. And then another contribution by Wonatsu and Yamagata, where they look at these factor models and how to estimate them. So this is sort of like understanding how we are thinking about factor strength. Now, turning to practice, generally speaking, we do not know this value of alpha. So if we were to use as our assumption that alpha is equal to 1, and this is it is incorrect, then in essence the inference that follows might be misleading. On the other hand, if we are studying factors that have alpha less than a half, then really these are being absorbed in the error term and there are of little consequence to our analysis. The factors that are of more interest and of more consequence to economic and finance problems are those that have strength between a half and 1. So just to give an example here, if we're looking at asset pricing models and we're interested in estimating risk premia of candidate factors that are likely to enter into our model, this paper by Pesseran and Smith shows that the identification and estimation of this risk premia are very closely, they are related to the factor strength. And how is that? Well, basically the rate of convergence of the risk premium is given, they show it to be n to the power minus alpha, which is our exponent divided by 2. So you get root n consistency if alpha is equal to 1, but for alpha less than unity, then you have a lower rate of convergence. And the lower the alpha, the worse it is. Unless, of course, you have a very high n, but this might not be the case in examples that people are studying. Now, this notion of strong and weak factors has sort of like gained traction in recent financial studies, and I'm giving a couple of examples here. And of course, similar considerations can be thought of when we're looking at macroeconomic shocks and how pervasive they are, and clearly the precision of our estimation, what sort of bearings it has on forecasting policy. So, in a nutshell, this is how we explain the importance of knowing the strength of factors from a theoretical and then practical point of view. In terms of what we're doing here, we are proposing an estimator to be able to quantify this factor strength. And we establish its asymptotic distribution when alpha is greater than half. And this estimator is based on the number of statistical significant factor loadings. And in doing so, we also take into account the fact that there are a bunch of tests. So we have an issue with multiple tests. So we take care of that. As I said before, we look at both the cases of observed and unobserved factors. And once we have gone through the theory, then we have small sample properties that we look at. And then we look at a couple of empirical examples. So, starting with the single factor model, going back to where I started from with our single observed factor model, as the simplest case, as I said, we are focusing on these factor loadings, gamma I here. So what is it that we assume about these? Well, we split them into two groups. Those that are non-zero, so in absolute values, these loadings are greater than a constant C. and this is for n to the alpha units out of n in the panel, while the remaining ones are set to 0. Now this can be relaxed slightly, but we keep the equal to 0 setting just for simplicity of exposition. So this exponent alpha here basically measures the degree of pervasiveness or strength of this specific factor in this simple setting. Then what do we do? How do we estimate our estimator? So we need to build that. So what we do is basically we run the n regressions that we have for our panel, and we obtain our estimates of the various coefficients in our model, and we are interested in the significance of the gamma coefficients. And basically what we do is we look at the t statistics for each of these, which is defined in the usual way. So once we have done that, then we compute our estimator, alpha hat, which is equal to this alpha tilde, which is basically equal to unity plus this fraction here. So what goes into this fraction is you have this p hat here, which is basically the proportion of regressions that have statistically significant gamma I coefficients. So we define it as in this equation 5 here, and we take the log of that in expression 4, which we divide then by log of n. And this is in the case where p actually is greater than 0. In the case where there are no statistically significant gamma coefficients, then we set alpha to be equal to 0. Now, the importance here is, of course, selecting, identifying the non-zero, the significant t-stats. And in doing so, we need a critical value. Given the multiple testing issue that we are facing here, in essence, we adjust this critical value, the usual critical value, which uses the inverse of the cumulative norm, and you have this nominal size of p divided by 2, where we have this adjustment here of n to this delta, which is greater than 0, and which I will discuss in a little bit more detail in a minute. So this is how we construct our estimator. A couple of points to say about the estimator itself. So these two, alpha hat and alpha tilde, they are asymptotically equivalent. But other than that, one could argue in favor of using this P, the proportion of non-zero loadings, as this measure of factor strength, rather than the exponent alpha that we are using instead. Now, these two measures, they're actually related to each other in the sense that P is equal to n to alpha minus 1. And, but what happens here? So unless alpha is equal to unity, in which case they coincide, if alpha is less than 1, then P basically decreases as n rises towards infinity, and eventually it tends to 0. We consider that alpha is a more discriminating measure of pervasiveness because it really measures the rate at which P goes to 0, rather than just the fact that P sort of tends to 0, which happens for any alpha which is less than 1. So that's just something to stress about our estimate. In terms of the asymptotic distribution, just to point out, in order to provide insights, for now, I'm just assuming that the error variances are known and the errors are Gaussian, which of course, we sort of use non-Gaussian errors and unknown sigma i's in our formal derivations. If I set the true parameter of alpha to be alpha 0 here, I have two cases. So in the case that alpha 0, the true strength is equal to 1, so you have a strong factor, then we have for our estimator here that basically it converges to its true value at an exponential rate here. So the distribution becomes degenerate, and we call this ultra consistency as opposed to super consistency, which has a sort of slightly lower rate of convergence. So this is a special case here, and it is boundary, of course. We're looking at the case of alpha is equal to 1. Now, in the case that alpha 0, the true alpha is less than unity, then we have this normalization by Cn here, which is given in this expression 8. And here you can see that this is this relates. It depends on this delta exponents that we sort of pointed out earlier on. Given this normalization, then you have this converges to standard normal distribution. In addition to this, we have this slight bias term here, which includes also.
Natalia.
So, yes.
Is this an okay time to take a couple of questions? We've got a couple.
Absolutely. Yes, yes.
Okay. We have 2 people with their hands up, so I'll call on the first one to have raised her hand. Maria Helena Vega. I'll unmute you, and if you would like to ask your question, you can go ahead.
I'm sorry. I by mistake I put the hand up.
Okay, no problem at all. We're all learning this Zoom stuff. On to the second person. Let's see if he or she. I only have the name Fersen here. I only know one Fersen, but it might be a different one. If you would like to ask a question.
Yeah, hi, thanks. This is Wayne Fersen here in Los Angeles. I'm wondering if you could comment on the role of factor rotation here. You know, we know that in many settings, when you have more than one factor, they can only be identified to within a rotation. How does this play in your setting?
So that's a very good question, and I'm actually going to discuss this in a few slides. So for the time being, I'm analyzing the case where the factors are observed. And so this is not an issue at this stage, but once we turn to the unobserved factor case, then this is an issue, and I'm going to discuss it. If you give me a few more minutes, I'll get to that.
Okay.
Okay. Shall I continue? Oh,
yes,
yeah?
please.
Yeah, all right. Okay, so what do I want to say about that? Right, so in terms of this delta that shows up in this convergence rate of our estimator, what values can that get? Can that take? So in terms, so if alpha, the true alpha is close to unity, then we just need that delta is greater than 0, and that is sufficient. As the value of the true alpha reduces, becomes lower, so tends to half, then you need this delta to basically be greater than half. And if you don't know, of course, the true value of alpha 0, then we suggest that setting delta is equal to half is sufficient. And in practice, the factors that we're actually interested in are the ones that are on the stronger side. So anything above like 2/3 and up to unity. And in this case, delta is equal to 1/4 is sort of works pretty well. Now we have done a robustness analysis of this, of course, in Monte Carlo, and delta in the range of 1/4 to 1/2 works pretty well, and it's quite robust. So that's the role of delta as it shows up. Now, in terms of formal analysis, we actually look at the multi-factor case where the factors are observed, I stress again. And really, it is a straightforward generalization of what I have just discussed. So I'm going to go through this quite quickly, but I'm going to spend a bit of time on the assumptions. So in essence, what has changed here is that we have an m-dimensional observed vector of factors, and this m is fixed. And we have loadings attached to each of the factors clearly. So the assumptions about the loadings really change in terms of adding a j, where j is basically the jth factor. So in essence, we have m values of alpha, which we want to estimate. The estimation strategy is exactly the same as the one that I discussed a minute ago. So in essence, we run our panel data regressions, and we look at the t-statistics, so significance of the loadings coefficients. So we look at the t-stats in exactly the same way as before, but we're doing this for each of the factors and for each of the units. And given that we have that, then we can construct our estimators for alpha for each of the factors j, again following the exact same steps as we did before. And of course, again, we look at the multiple testing problem. Now, in terms of assumptions that we use here, we have two main ones. So we have that for the error terms here, and for the demeaning factors, we assume that they are multiple difference processes. We have for the variance covariance matrix of the factors normalization to identity. And then the errors, we assume they are independent over I, and of course with relation to the factors, and that they have constant variances. In terms of and then we move on to assumption 2, where basically we look at the tails of our observations, so XIP, and the factors, which basically they have pretty thin tails. So these are the assumptions that we use in deriving the asymptotic distribution for our estimators alpha hat j. So this distribution is pretty similar to what I was discussing, and the only change again is basically that we're looking at the strengths of individual factors, where we have m of them. Just to say a couple of things about the assumptions that we used. So these can be relaxed, and one way is in terms of the error terms, so they don't need to be independently. You can have spatially dependent errors, and the central limit theorem will go through. In terms of assumption 2, instead of these thin tails, you can think of suitable moment conditions, and given these, derive a bound on the variance psi that we have there. And then again, for the multiple difference assumption for the factors, you can think of a mixing assumption that has been analyzed in Chadwick and Cole. In terms of the test that is based on our estimator here, just point out that it is going to be a conservative one, in the sense that the rejection probability under the null will be bounded by the significance level. And this is because we cannot get the asymptotic approximation of the variance, but rather an upper bound. So this is what we get in terms of that. Now moving on to the unobserved factor case, which is what was mentioned here. This is more tricky as a setup, and the reason is exactly what was identified, that basically latent factors are identified up to a non-singular rotation matrix Q. And just to sort of be a bit more precise about the issue here, because here we're interested in the strength of the factors. So the strengths can be identified, it's just the factors cannot. So assuming that you have two factors, F1 and F2, and they have strength alpha 1 and alpha 2, they're both above a half, but the first factor is stronger than the second one. So that's what we are assuming here. And basically we have that the two factors, F1, the true factors, and F2 are a linear combination of the PCs that you extract. Given that this rotation matrix, and then the estimates of the factor loadings are basically given to you, given this expression here. So in essence, you have for the principal components that they converge to true factors, and then you have this Q-1 matrix, and you say the exact same thing in terms of the loadings themselves. So it can be that the estimates of the factor loadings, they will not provide consistent estimates of the associated factor strengths. So this is the issue. And to be even more precise, if we write down the estimates of the factor loadings for the first factor and the second factor, and we square them and sum them, which is what we discussed at the beginning of the talk, in essence, what we have here is that both these quantities will rise at the rate of n to the alpha 1, which is basically the factor that dominates, which is the strongest one. So this is the issue that we have here. one could consider looking at covariance eigenvalues, but here you have the issue that the eigenvectors themselves are not uniquely determined. So given this issue, as a starting point, we can definitely talk about the strength of the strongest factor, so the one that dominates, and we can estimate the strength of that using this estimator that we have built. We can do the exact same thing, of course, using the estimates that we have already developed in our previous two contributions, but we have checked that you can actually do the same using this approach as well. So what do you do in these regressions that we had on a constant and the factors that we have been looking at? When replacing, in this case, we're replacing the observed factor with the proxy of the unobserved one. And what you can use is either the first principal component or the simple cross-sectional average of the units that you have in your panel, or a weighted cross-section average of these, where the weights are basically slope coefficients of your simple cross-section averages that come from a regression of the XITs on an intercept in this cross-section average. So there's three ways that you can go about this. And basically reformulate the setting by sort of splitting the strongest factor, so the first one, FT, sorry, and then you include the remaining factors in the error here plus an extra. Okay, and similar assumptions about the loadings, of course. So here you're assuming that n to the alpha 0, so this is a strong factor, that the loadings load on n to the alpha units, and then the remaining ones have got 0 loadings. And you have the same for the other factors where alpha j is less than the strength of the dominant factor alpha. You follow the exact same steps that we did for the previous setting, for the observed case. In this case, you're looking at this t-stats of the coefficients of the cross-section averages. So this is the one that we have used in this case. And again, build our estimate in precisely the same way, where we're basically looking at the fraction of significant loading coefficients, taking into account the multiple testing problem. So this brings us to our second theorem here, where basically, given the assumptions that I discussed beforehand, we have this expression for the asymptotic distribution. In addition to what we have discussed before, we have this extra condition here, which basically tells you that our estimator will work better the larger the difference between the strength of the strongest factor and the one sort of that follows it, and as n increases, of course, and the rest is sort of similar to what you have seen before. Now, if you were to think about getting some information about the strength of the next factor down, so the slightly weaker one than the one that dominates, then one can think of a sequential procedure where you can use weighted cross-section averages. So in essence, what you would do here is basically run Euler's regressions of your XITs on an intercept and the simple cross-section averages, and then take residuals of that. And then by doing that, then you would take weighted cross-section averages, because the simple cross-section averages would basically sort of tend to 0, and then look at the t-statistics of the relevant loadings, and given that, you can construct an estimator of the second factor slightly weaker, and we denote that by alpha 2. And sequentially, you can do the same thing. You basically take residuals of another regression so that you can look at the next factor strength and so on and so forth. In terms of conditions, the condition that I discussed beforehand, in essence, you would look at the difference between two successive factors, and you would want that to be as large as possible. And again, this works better as n increases. In terms, how long do I have?
You have 7 minutes left.
How much?
7.
7? Okay, well, I will go through the small sample properties pretty quickly because I think the empirics are quite interesting. So clearly we go through a number of experiments in terms of testing our estimators. So we have a 2-factor setting where we assume the factors can be orthogonal or correlated with each other. We look at a Gaussian case for the errors, a non-Gaussian, and we generate the factor loadings such that n to the alpha 1 and n to the alpha 2 of these units have gone non-zero loadings. So we have a bunch of experiments here, 1-factor models, 2-factor models, observed, unobserved. In general, the results are pretty similar. And wherever I have made remarks in the theoretical part, they basically, the simulation results reflect these. I'll just pick one experiment, so a 2-factor case where we have observed factors and where we have non-Gaussian errors. And here I've just picked the case where the second factor has got strength of 0.85, and then I'm estimating the strength of the first factor, which ranges from 0.75 all the way up to 1. So in terms of bias and root mean square error, generally speaking, they're pretty low universally. They also decrease as the sample sizes increase, and also as alpha tends to unity. When alpha is equal to 1, you see there's pretty much nothing here in terms of bias and root mean square error, which confirms the ultra consistency that we discussed before. In terms of size, you can have some distortions in the size, especially when alpha is sort of like lower, and that is due to the precision of our estimator. So it gets affected by the bias that our estimator has. But as alpha again increases, then that goes away and you have a nicely behaved test. In terms of power, looking at a moderate t of t equals 200 and then having n rising from 100 to 1,000, you can see that our estimate is has pretty strong power, especially as alpha increases. I'm going to skip the rest and I'll move on to our empirical, and I'll just pick the finance example here. So we're looking at asset pricing models and which factors do we want to use in, we want to select in our asset pricing model. So we're not really looking at the selection problem here, but more we want to compute the strength of candidate factors that we might consider adding to our CAPM or extension of that. And the aim here, of course, is identification and estimation of risk premium. So when looking at the Farmer-Macbeth 2-pass procedure, in the first step, you need to select the risk factors that enter into your asset pricing model. Now, clearly, there have been a number of factors that have been suggested. Harvey and Leo document 400 of these. And there is a growing literature, sort of area in the finance literature that evaluates the contribution of these potential factors in these models. So we relate this to the work of this paper of Pesser and Smith, which basically discusses this rate of convergence in terms of the risk premium. And I think I discussed this beforehand, so I'm not going to go through the same thing. Just moving on to the data and what it is that we're actually doing. So we're using constituents of the S&P 500 index in each month from September 1989 to December 2017, and we compute monthly excess returns here. We do a bit of cleaning of the data and we end up with roughly 442 securities in each month on average. So this is our panel. In terms of the factors that we are considering, we have 146 in total. So we have the market factor, which is measured by the excess market return. And then we have an additional 145 that have been considered by Feng and his co-authors. In addition to computing the strength of these factors, we also want to see whether this strength varies over time. So to do that, we actually consider rolling samples of 10 years over our whole sample. So that gives us 340 rolling samples. So what we consider is we look at the original CAPM model, where we are only sort of regressing the excess returns on a constant and then the market factor. And we also look at the extended version of this, where basically we add one factor at a time. And so we have 145 regressions. So what we're interested in seeing here is, well, what is the strength of the market factor? Is there an effect on the estimate of this market factor, of the strength of the market factor, if you include extra factors here? And then we're also interested in computing the strength of the additional 145 factors. So just to summarize the results here, in this first figure here, we compute the strength of the market factor from the CAPM model, the original one. So this is the red solid line here, and how it evolves over a sample period from 89 to 2017. Now we have magnified the scale here. So the scale goes from 0.94 to 1. And we compare this series to the strength of the market factor that comes up out of the 145 regressions that we used, where we were basically switching the additional factor. And we took the average of that. So 2 points to make here. Generally speaking, the strength of the market factor is pretty much unity throughout, but you have sort of some deviation from this from unity around this middle period here that can be related to a number of financial events that took place around that. Now, the two series track each other pretty closely, which suggests that the effect of adding an extra factor does not really make a difference to the estimates of the factor strength in terms of this one. Moving on to the second figure, here we're interested in the remaining 145 factors and how strong they are. So we summarize their strength in terms of how many of these factors breach a number of thresholds over each of the periods, the months that we are looking at. So the thresholds that we have picked are 0.85, 9, and 0.95. As we increase the threshold, the number of factors that exceed this threshold drops, and really there's no factors apart from a blip here, which exceeds this 0.95 threshold. And finally, I think I'm running out of time here, we have included a ranking of factors in terms of the percentage of months in which the alpha estimate is above 0.9. So we have ranked all factors, of course, and this is shown in the first column here. And we have that the market factor, which is the one at the top, basically exceeds 0.9, 100%. And the second one down exceeds the thresholds a much sort of lower percentage than the market factor, and so on and so forth. Next to these, we basically give averages of the alpha estimates for the full sample and 3 subsamples we're looking at to sort of quantify the strength on average in these periods. Just as a final point, in terms of the Fama-French factors, so size and value, the value factor ranks 34th in this list. It's actually below what I'm showing you here, so not very high. And the size factor actually does not even rank, so it never exceeds 0.9, which is quite interesting. Okay, do I have time for one final point, or shall I just conclude? And yeah, so just as I'll stop here, but as a next step, it's basically interesting to look at, now that we know the strength of these factors, how do I select which factors to enter into my model and take it from there. And I'll stop.
Okay, thank you very much, Natalia. Well, we'll go on to the discussant. The discussant is Simon Freyaldenhoven. So if you'd like to share your screen, Simon, you can take over.
Okay.
Yes, that's great.
There you go. All right, so let me start by thanking Andrew for organizing this, and then Natalie for writing a fun paper. So that was actually a pleasure to discuss. So thanks for that. So I'm going to start with sort of a very standard factor model that you're familiar with, and sort of build to the model that's in this paper. And so I don't have to go through the notation, but sort of as Natalie alluded to, the standard assumption in factor models would be that essentially on average, these coefficients gamma, or these loadings, are going to be non-zero. So this sort of thing in the bracket here is formally the same, but you can think of that as saying the average loading is not zero. If you've seen sort of weak factor models before, particularly since this is a SoFiE audience, you might have seen this in this sort of Kleiberger 2009 kind of sense. And usually the way these weak factor models are derived there is that you think about these coefficients, these gammas, and you put drifting sequences in there. So this is very much like a first stage in a weak IV kind of paper, where you just think of these coefficients as drifting towards zero, usually at 1/square root n. And of course, that also that means that no longer the average loading is sort of bounded away from zero, but it drifts towards zero here. This paper is sort of taking a different approach to weak factors. So what we have here is this is the setup of this paper, as Nelly explained earlier. We no longer have this case where all of the factors, where a factor affects weakly everything. We have these drifting sequences of coefficients where there's a very small effect. But instead, a factor is strong, but only for some of the outcomes. So it's sort of the regular type of strong factor on a subset in a particular industry or something like that, and it's zero everywhere else. So that, of course, is the same effect. On average, that loading is no longer bounded away from zero, but the average loading sort of becomes close to zero. And then in this paper, we're interested in this alpha exponent, which is synonymous with the strength of this factor. Now, of course, a naive approach to this would just be to say, and I think we also talked about this in our talk a few minutes ago, a naive alternative would be to say, okay, why can't we model that through this proportion pi and saying only 10% of the outcomes are affected by that factor, and that makes it weaker or sort of local in that sense. And the problem, as you pointed out, is that as long as the proportion of affected outcomes pi is fixed, doesn't go to zero, all factors asymptotically are strong. So the sort of the standard condition holds, and there isn't really much we can do from an asymptotic point of view, from a theoretical point of view. So I think thinking through this factor strength through this exponent alpha seems like a good idea. That's sort of the only way we can get at this notion. We can say anything really from a theoretical point of view. Now, the first point I want to make is essentially that you can still think of this as a drifting sequence framework. So if you think about this pi parameter as being the proportion of outcomes that are affected by a given factor, that thing becomes our drifting sequence here, and it drifts towards zero for all values of alpha that are equal to 1, right? So fewer and fewer, as a proportion of all outcomes, fewer and fewer outcomes are affected. And so usually when we use these drifting sequences in economics, we can think of that as a device to approximate some sort of finite sample behavior of an estimator or something like that afterwards, right? It sort of serves a better approximation. I already mentioned weak IV, where you would sort of pick the convergence rate of the drifting sequence. We shrink the coefficient in the first stage at a particular rate, usually 1/square root n, and that gives us this sort of balance between sampling uncertainty and signal. So here, thinking about it that way, this alpha, what we're interested in is really the convergence rate of that drifting sequence. And so I'm sort of a little bit torn here because on the one hand, as I said, I think this is the right way to model this. I think this is how we should model this to say anything. But then it sort of becomes this object that's not immediately clear to me why it's a sort of why it's the object that really is interesting in economic models. So it's this, we use this as a tool to approximate some distribution, but here it's not the distribution itself, but here's this convergence rate we're interested in. And I think you actually did a nice job in the talk about some reasons why we care about this, which is maybe not as clear in the paper right now in the draft I've seen, but sort of talking through a few more examples why it's really helpful to be able to put bounds on this alpha. We can now test whether it's 2/3 or 0.75. would have been helpful for me, talking through some of the implications of having different rates. In particular, within this range of 0.5 and 1 that you can really use your statistic. Going back to the framework, then the paper distinguishes two cases. So the first case talks about observed factors, and then the second part of the paper talks about unobserved factors. So I'm similarly gonna have a comment on each of these two sections. So for observed factors, I think the distribution results are really nice. I'm not gonna have much to say about the theoretical results. Intuitively, we're running n regressions and we're counting significant coefficients. Of course, it gets more subtle than that, and the paper does a very nice job at deriving inferential results for that. So the comment I have is more sort of on how we can extend that. I see the assumptions being somewhat restrictive right now, and I think I'm not sure all these assumptions are needed. So you might be able to make these things more widely applicable. So the first thing you talk about is you need this orthogonality of the factors, even in the observed case. If I think about that finance application, it's not completely clear to me why that's plausible, why these factors would be orthogonal. And these are really basically one big comment. I think they're all related, as I'll talk you through in a second. Second question would be this number of factors. It wasn't quite clear to me if that has to be known a priori and if it can depend on the sample size. I think in your application, as you said, you use 145 factors. That might suggest you might want to index that with the sample size. And then also related to that, I think in the theory, you basically develop everything for this multivariate regression of xi on all of the factors. But then in your finance application with 145 possible factors, that becomes tricky to the degree to a point where it's not even feasible, I think, with t equal to 120. I think what you do in that application is sort of run these univariate regressions on one factor at a time, which, if you maintain this assumption one where the factors are orthogonal, maybe that's fine. And so you can get rid of that assumption. At the same time, if you do run a regression on all of the factors, maybe you can get rid of this orthogonality assumption. So to me, these seem very much linked. And if you had to maintain all three, so you have to know a priori how many factors there are, that number has to be small, and the factors have to be orthogonal. That seems quite restrictive. But it seems like there's room to relax, at least in one or two dimensions at any given time, although I wasn't quite sure. So I'd be curious what you think about that. Okay, so then unobserved factors. Oh, I have a few minutes. Okay, perfect. 2 minutes, right? Okay, so unobserved factors, which I think, so the limitation there right now, again, I think it'd be, you develop all this machinery, and it'd be great if you can use it for more than just estimating the strongest factors. And the reason, of course, you can only estimate the strongest factors because this rotational indeterminacy that we talked about. And so ultimately, this proposed estimate here becomes an alternative to some of the earlier work that estimates that alpha 1 already. And so I thought a little bit about what we can do about this rotational indeterminacy here. And so essentially the issue is that, there's observation equivalent models, and you can rewrite this loading matrix gamma here in matrix notation. You can multiply it by any non-singular matrix A. You can also redefine the factors, and you have these observation equivalent models. And it's true that without any further structure, this is, that you can't say anything about that. And so what that means is that any estimate in general is going to estimate some rotation of the truth, some rotation matrix Q. Now, that's in general true unless we're willing to assume more things about the loading matrix of the factors. So there's sort of the Binding 2013 paper points out that if we actually knew that for the true factors in the true loading matrix, these conditions, this orthogonality here holds, then we don't have to worry about it. Now, these are very sort of ad hoc assumptions, and I'm not sure there's any reason to think of these factors, and particularly the loading vectors, to be orthogonal. But there's other structure you might be able to impose. And so I have a recent work where I think about what can we learn from the fact that this loading matrix is sparse. And so the idea is sort of that, there might be two observation equivalent ways to write the structure down here. But if once you rotate this first matrix gamma that may be sparse with some non-singular matrix H, you lose that sparsity. So you can use the sparsity to identify the right rotation. And in this paper, you already assume sparsity, right? Because from the beginning, you can think of this drifting sequence as saying actually almost all of the coefficients in a given vector are 0. So you have a very high degree of sparsity here. And my sense is you can probably use that sparsity assumption to identify the individual loading vectors or the individual factors. And if you can't find that, then there's so as your model is misspecified. There is no sparsity essentially. And I think I'm basically running out of time, so I'm going to skip through this. I'm just going to say, the theoretical results are very nice. I think the inference results are particularly neat. And so I like the theoretical results, and I got excited about them. And I think there's sort of some of the assumptions maybe you don't necessarily need, and it would be nice just to expand the scope a little bit and weaken the assumptions a little bit. And I'm excited for sort of future iterations and maybe follow-up papers that do that, because I think there's wider applicability than what you can show in the paper right now. I'm excited to see those results. All right, thank you.
Thanks very much, Simon. Well, Natalia, if you'd like, you could take a couple minutes or take whatever you like to respond, and then we can go to the audience for questions.
Yeah, thank you very much, Simon, for your comments. I'll just pick a few. So the issue that you mentioned about the weak factors defined as being basically the ones so that all sort of like factors are scaled downwards by square root of n. So this is something that we sort of touched upon in earlier work, and we just consider that having a number of units that are sort of affected by the factor and the rest are not. We consider this to sort of be a more, to conform to sort of empirical applications that we have seen a bit more than the other ones. So this is why we go down that route.
I fully agree with that, by the way.
Yeah. So that's how we thought about it. In terms of now, in terms of the factors, so we assume that they are fixed. So I mean, what you are suggesting is actually true. So we're not looking at, we're not extending this to the factors being a function of n at this stage. The way we thought about the empirical application was we're adding one factor at a time in addition to the market factor, which we know is strong, having in mind the one covariance at a time method, for instance, where you do with it one at a time. So that is not an issue. But you're absolutely right that you might want to generalize this in looking at like a large number of factors, but we don't go down that route at this stage. But that's something definitely to look at. And your sparsity idea, I have read your paper, and it is interesting. So we are in the middle of revising the paper right now, and what we have been working on is this sequential procedure. So basically, you take residuals sequentially and then estimate it in that way. But the sparsity sort of idea is something that maybe we could explore. It sounds like a nice idea. Is that, yeah, maybe, yeah. Assumptions we can look at. I think the normalization was just made for simplicity rather than anything else. In the Monte Carlo simulations, we also assume that factors are, we study the case where factors are also correlated. And
yes, exactly. So I saw it works well, which is one of the reasons I think you might not actually need that, and it looks more restricted than I think it is.
We can, yeah. Thanks. Yeah, that's.
Well, we've got a couple of questions from the audience. If
Okay.
so we'll squeeze in these two before we close. So we have Wayne Ferson has a question, and I'll ask him to go first.
Okay, thanks. I had actually a comment and then a question. The comment is I enjoyed the empirical work, but one would be interested to know why there became this extra market covariation at the turn of the century, and it has since gone away. I mean, a little more specifically, why would really enhance that empirical work. Now the question, and I hate to go back to this again, Simon hit on it too, is this rotation problem. In your observed factor case, the assumption of an identity covariance matrix for the factors already, I think, implies a certain rotation. So, you know, it's not so bad in your example with the market and additional factors. I just think it means it's the projection error of the additional second factor on the market that you're sort of evaluating, right? But when there's multiple factors, it seems to me that that rotation destroys the ability to attach importance to any particular factor. And doesn't it throw the analysis into the same situation as the unobserved factor case in that sense? That's my question.
So I need to think about this. I'm not sure about this. I mean, maybe what Simon is suggesting, what you are saying, is correct in terms of the assumption, the orthogonality assumption that we have of the factors. I understand. I mean, we are assuming that the number of factors is, at least in terms of the application, I'm going to reiterate what I said beforehand, that basically we are not adding too many factors and checking what happens to the estimators of these factor strengths if you do that. We have not looked at that, and maybe it is something that we can look at and see what happens. So the intuition is basically what I suggested beforehand in terms of the selection of the CAPM specification that we are using. But I need to think about this.
Okay, we have one
Oh,
final question.
yeah, okay, sorry. I forgot he asked another question, didn't he? About the reasoning, was it the reasoning why the strength sort of deviated from unity? Was that the question? Or maybe not, I'm not sure. It's the first part of the question.
Am I up now, Andrew?
Okay, never mind. Yeah, we can move on.
Okay. I just have a comment that maybe you want to address now, or maybe you don't want to address now. That there's this, maybe you mentioned this paper by Svetlana Bogosiev and several co-authors who do this massive Bayesian analysis of like 15 quadrillion different models. And what you learn at the end, which I think is an excellent paper, but most of the posterior mass lands on the Fama-French factors, which I interpret as not surprising because the profession has been beating against those data sets for the last however many years, and it's it's not that they actually discovered that where the mass of the posterior is through this gigantic professional trial and error process. Now, economists sometimes get puzzled by the Fama-French factors. Maybe not so much book to market because you relate that to Tobin's Q, but some of those other ones really seem. And what I really liked in your papers, if I looked right, you took a set of economically interesting factors that I think were different than what Rigliosa, that's Svetlana and her co-authors did. They drew theirs, I think, from the literature, and you got yours. I don't know exactly how, but anyways, I think finance economists are going to want some kind of reconciliation between that paper and your results, which I think would be quite interesting. And you can postpone, you can wait and see. I don't need an answer now.
No, absolutely. So I know about this paper, and there's a similar paper in Macro by Giannone and co-authors, which I think follows similar approach. I mean, they're looking at factor selection as far as I understand. So it's slightly, and I absolutely agree that these problems are linked, but what we are focusing on here is basically measuring the strength of the factor. And it needs to be linked to the problem of factor selection, which we do not do here. And that is an interesting avenue for the next contribution. In terms of the factors themselves, we basically borrowed them by this paper by Feng and co-authors. So they were kind enough to provide these factors to us. And they're basically long-short portfolios of stocks that are based on various characteristics of the stocks, basically. But I know about this contribution. I mean, maybe I leave it at that. So there are a few.
Yeah, you could leave it at that.
It's not exactly the same. I absolutely agree with what you're saying, and it is a very interesting comment. But we have not reached that stage yet. So. For this specific paper, we're looking at an estimator that gives you the strength of the factor. Whether you're implicitly getting that, so I suspect that this is what you're suggesting, It's not 100% clear to me. So they do not assume heterogeneity in the betas, am I correct? So they're pooling the beta in doing this approach.
I don't remember. I don't want to put words in their mouth.
Yeah,
I haven't read the.
So it needs further analysis, basically. I'm not sure that I can sort of comment further on this.
As I said at the beginning, that's fine.
But thank you for this. Thanks.
Okay, well, this seems like a good time to end the official seminar. If you'd like to stick around after we stop the recording, then please do, and we can have a more informal discussion about the paper and other questions that might have come up. So I want to thank Natalia and Simon for the presentation and discussion today. I think it was great. And before we go, I'd like to do a little advertisement for the next SoFiE seminar. The next SoFiE seminar is our 10th, and it's going to be a special edition for PhD candidates on the job market. We're going to have 4 speakers: Gianluca Denard from Zurich, Philippe Goulet-Coulomb from Penn, Hyun Jung from NYU, and Merrick Lee from Cambridge. We won't have any discussants. Each of these will have 20 minutes to present their job market paper, or a very brief version of it. And there'll be time for questions, so it'll be a little bit longer than our normal 1-hour slot. It'll be about 1 hour and 20. That'll be in 2 weeks' time on October 5th. So please join us for that. And with that, we'll end the official seminar for today.
Thank you.